All right, Mr. O'Brien here, and today I'm going to be giving you guys a short video about the different types of chemical reactions. Okay, so scientists, and that includes chemists, we're trying to make sense of the world around us, so it helps to kind of sort things and organize things, and we can do that with chemical reactions too. So we typically break those into about 4 or 5 groups. I'm going to talk about 5 types today. That doesn't mean there are some reactions that don't act as exceptions to these rules and fall outside of these categories. But today I'm going to cover 5 main reactions. Okay, and I kind of like to think of these things almost like relationships. Okay, it's all about getting together, falling in love, breaking up sometimes. So the first reaction that I'm going to talk about today, or the first type rather, is called, let's do that in black ink. It's called a synthesis reaction. Okay, so synthesis means kind of like making or manufacturing or assembling something together, and that's what we're doing here. This is the start of a new happy relationship. Okay, I've got my 2 reactants, and these could be really any compound or really any element. All right, but I've got my reactant A and I've got my reactant B, and they're off doing their separate things, living their own lives, but they meet in a beaker or out in nature or come into contact with one another somehow, and they fall in love, and they're going to form a bond together, creating a larger molecule, a more complex substance. Okay, so we're adding A plus B to create AB. That's a synthesis reaction. Okay, the opposite of that is breaking up. Okay, we call this a decomposition reaction, because what happens when things decompose? Well, imagine, you take a banana peel or something like that and you throw it in your compost and it decomposes over time. What is it doing? It's breaking down, okay, or it's breaking up. So this is the opposite. We're starting with a large molecule, large substance here, and we're breaking the bonds. We're separating. Sorry, it's time to go on, move on with your lives. And we're going to get smaller products than the reactant we started with as the result of that decomposition reaction. All right, the third reaction I'm going to go over today is called a single replacement reaction. Okay, and this is when it comes to relationships where things get a little unconventional. Okay, so imagine in a single replacement reaction. Imagine that you're already, in a relationship. You're already partnered up. You're happy. You've found someone that you want to be with. In this case, A has found partner B, and they've joined together in a relationship. They've formed a bond. They've created a compound or a molecule. Okay, but all of a sudden, there's trouble on the horizon. In comes this femme fatale or man mystique here. And all of a sudden, A doesn't seem so happy with B anymore. Instead, A is going to, I think, find C a little more attractive. Okay, and these two are actually going to form a bond and create a new substance here. So in this case, B has been replaced by C. Okay, so AC is one of the products, and then poor B got booted from the original relationship over here, and now B is a lonely guy by himself over here. All right, things get even a little more crazy when we start talking about double replacement reactions. And I'm going to give you guys examples of all of these different types of reactions in just a minute. Okay, so in double replacement reactions, you can imagine like you're out on a double date. Okay, so in this case, let's picture we're A and we're here with our boyfriend or girlfriend B. And we've gone out to dinner. Social distancing is over. We can go out to eat again. We're on a double date. We've brought our friends C and D here. And C and D are also in a relationship. Okay, but as the dinner goes on, we start to argue with our significant other. We see, maybe these just aren't the people that we were meant to be with. And you know what? Maybe actually D over here is looking like he or she is maybe potentially a better person to be with. So in this case, we're actually going to trade partners. No one's going to be left out of this, okay? A and D are going to become a new compound over here, and then B and C are actually going to form a new compound or a new molecule here. So what's happened is that both of these reactants have come in, they've broken apart, kind of traded partners, and become two new products over here. Okay, and let's go ahead and look at a few of these with examples. All right, so a great example of a synthesis reaction. This was in your reading that you guys did from one of the handouts that I pushed out to you. And a great example of this is the formation of rust. Okay, so in the reading that you guys did back at the beginning of the week, or actually, I'm sorry, the beginning of last week, you saw an image of a boat that had washed ashore and was rusting. Okay, so in this case, you can imagine that that boat is made up of steel. And steel is an alloy. It's got some carbon, but it's mostly iron. Okay, iron is this Fe right here. Okay, so we've got this pure metal iron, but it's sitting out there, it's getting rained on, and it's being exposed to oxygen, okay, oxygen or O2. Okay, and essentially what's going to happen is that these two things are going to come together, and they are going to form iron oxide. It's going to be Fe2, and keep my colors the same here for you, O3. And this isn't balanced, but I'm not going to walk you guys through every step, but if we were to go ahead and balance that, make sure that we're not gaining or losing any atoms here, we're going to end up with 4 iron atoms plus 3 molecules of oxygen will produce 2 iron oxide compounds. Okay. The next reaction I'm going to talk about is called a decomposition reaction. Okay, so again, a decomposition reaction, this is where, we're breaking up. This is the opposite of a synthesis reaction. Okay, so a great example of this reaction would be if we've got some water, for instance. Okay, so we've got water. In this case, we've got a happy couple between some 2 hydrogen atoms and an oxygen atom here. Okay, but all of a sudden, things aren't doing so well for the happy couple. Maybe we run some electricity through some salt water, and it's just the right voltage that it starts to break apart those bonds that hold the water together, and it's going to break it down into 2 smaller constituents or 2 smaller components here of hydrogen gas and oxygen gas. Okay. So we started with this large molecule here, and through a decomposition reaction, we ended up with 2 smaller products as a result. And of course, for those of you following and paying attention, want to make sure this thing is a balanced equation. We would need 2 molecules of water, and as a result of splitting apart those water molecules through decomposition, we'd end up with 2 molecules of hydrogen gas and 1 molecule of oxygen gas. All right, for the third type of reaction, we've got what's called a single replacement reaction. Okay, in this case, I'm going to use for my example here, I'm going to use an ionic compound to start. Okay, and this ionic compound is called potassium bromide. Okay, so K is the symbol for potassium, Br is the symbol for bromine, but it's an ionic compound, so we change that E to I. We've got potassium bromide. Okay, so potassium bromide, that's in a happy relationship with one another, but it's not meant to be, because when we introduce this third character here, we introduce chlorine gas. Okay, that chlorine is going to be a Budinsky. He's going to move in, or he or she, and take the place of, in this case, bromine. Okay, and as a result of that, after our reaction, our single reaction takes place, we're going to end up with a new compound called potassium chloride. and then bromine will be left out, okay, on its own here. In this case, it's bromine gas, that's Br2. And so in this case, for us to have a balanced equation here, we would need to add some coefficients here for 2 to give me my 2 bromine atoms, and then that would also produce with the double replacement reaction. Okay, in this case, we are going to use another ionic compound called silver. That'll be our A, nitrate. Okay, this will be our B. Okay, nitrate, that's what we call a polyatomic ion. So in this case, I've got an ionic compound where Ag or silver is forming my cation, and then NO3 is forming my anion. That's a nitrogen bonded to 3 oxygens, and it's got a negative charge on there, so it's stuck to that positively charged silver. Okay, so I've got one compound there. I'm going to add that now to another compound, our good old friend sodium chloride. Okay, and when we introduce silver nitrate to sodium chloride, again, these things are going to trade partners with one another. So in this case, A and D are going to form a pair, and then B and C are going to form a pair. So again, that's kind of like that double date where you don't end up leaving with the person that you went with. So in this case, silver doesn't leave with nitrate. Silver is going to end up with chlorine to produce silver chloride. And our sodium, Na, is going to end up with NO3, that nitrate, to make sodium nitrate. Okay, that's our double replacement reaction. And last but not least, this is a special kind of reaction called a combustion reaction. Okay, I wanted to include this because I know that a lot of you guys are doing combustion reactions as part of your everyday chemical reactions. So in a combustion reaction, this is a special reaction because, well, we're starting out with a special class of molecules here called hydrocarbons. Okay, this is what a lot of fuels are made of, particularly like fossil fuels. So like coal and oil and natural gas, things with names along the lines of ethane. Well, let's actually start with the simplest. Okay, we've got methane. That would be like 1 carbon bonded to 4 hydrogen atoms. Okay, we could have a larger molecule here like ethane. Okay, where we've got 2 carbon atoms, and then they're all bonded to 6 hydrogen atoms. And we could keep getting even larger and larger. Remember, carbon likes to make these big, long chain-like molecules. Okay, so we could just keep making larger chains or rings here. And again, these things make for great fuels. So think about things that you might burn on your stove. Propane, hopefully not methane, butane, ethane. Again, a lot of good energy sources. Okay, so we start with a hydrocarbon. We don't know how many carbon atoms there are. We don't know how many hydrogen atoms there are. I'm going to denote them with a variable here, X or Y. We don't know how many there are because it could again be methane we're talking about, or ethane. It could be just any hydrocarbon with any number of carbons or hydrogens. Could be 10, could be 50. And we're going to burn that in the presence of oxygen. Okay, so when you turn on your propane stove here, that's what you're doing. Okay, you're introducing your hydrocarbon fuel to oxygen in the air with a spark, and that's going to trigger a chemical reaction that's burning something. So combustion, that's a fancy chemistry word for burning. And this is always going to produce 2 products in particular. Okay, it's going to produce CO2. So again, that's usually released into the atmosphere as a greenhouse gas. So that's produced from coal fire plants and natural gas plants. and even produced from your campfire when you burn the hydrocarbons present in your firewood. So that produces carbon dioxide, and then this gets a little less press, but it also produces some water vapor in the process as well. So some good old H2O. So again, that's a combustion reaction, and depending on the number of carbons that you have present over here, X, and the number of hydrogens that you have present there, Y, in your fuel, in your hydrocarbon, that's going to determine what the coefficients are for your products, right? If I've got a bigger hydrocarbon here, then I'm going to produce more CO2 and more H2O. It's also going to take more O2 to burn it as well. Okay, so the size of that hydrocarbon, a lot of times that'll determine the number of oxygen molecules you need and also how many CO2 or water molecules you get. All right, that's it for me, Mr. O'Brien, signing off. Till next time.